Okay, so normally I'm like,
I bet I could build that in Minecraft. No, I don't have
but
problem.
I'm actually going to build it in Logic World. How's it going, guys? So today's video is going to be on some stuff I was making in Tong. Most of this crap was made a long time ago and I never made a video on it, so I figured I don't have much well, I have a lot of content that I can shoot on, but I decided to do this first. So I want to show you a fully synchronous 16-bit ALU, and that's this right here. So, oh, I got some lag there. So what this is doing is, we have this module here, stop guy. That there is invert A. The one underneath that is invert B. Then A and B come into the first XOR of the adder, or of the ALU, I guess I should say. And then there's a carry table. So this does carry look-ahead algorithm, and it does this synchronously, which means that each carry takes the same amount of time to generate as another carry. So C0 takes the same amount of time as C16, which is your carry out. So basically, what you do is you take all those carries and bust them up here, and then you take your propagates from your XOR and bust them up here, and then here's some more XNORs. So then those two values get XNORed together, and that's the sum of the adder. And then I added a downshifter device, which is this thing, or right shifter. So this will right shift numbers. So it's kind of hard to see when it's down like that. So instead we'll look at it like this, and it's up in the air because it's meant to be built vertically. So what I can do is I can put a switch here, do two switches. So on one input we can put, like, say 5. So there's the number 5, and on the other input we can put, say, 3, like that. So when I flip 5 like that, we should have a 5 coming out, and we don't, and let me figure out why. And the reason there was no output is because that wasn't hooked up. Alright, there's our 5. Alright, and then I could input a 3, and now we should have 5 plus 3 is getting 8, which it does. And what you can see is, I should be able to reach that from here. Yeah. So when I flip that on, you can see it carry. Look at the output here as I flip this switch over here. So you can see it's synchronous, going from 5 to 8. And I can change the tick speed down to like 5 ticks per second. So you can see as it propagates through, it's synchronous. It's not a ripple. Although I think, oh, maybe it's not synchronous, but it should be easy enough to sync. Oh no, maybe no, that is. Oh, it's not on the rising edge there. Alright, I might have to put a tick of delay somewhere in one of these carry lines, but that's not a big deal to make it synchronous. At least it carries without a ripple. So if I were to put in, say, now let's do this. Let's turn that off. Let's actually delete those inputs, and actually let's delete that. And let's tie this to the input of every single one, or at least a few, because 16 is going to be a pain in the butt to wire up right now. I'll show you what it means to have a rippleless carry. Alright, I guess I can hook them all up, screw it. One more. Okay. So when I flip this on, like that, now I should have all ones coming through the output like that, except one of these is missing, and that's because it's not hooked up. Alright, there we go. And now let me change this back to 100 ticks per second. Sorry for the dogs. Okay, so now you can see that we have ones coming through here, and when I flip a 1 on, the carry out will turn on here. So all these bits will turn off, and this will turn on up there. So my carry in is right there. So see that, and then that turned on and came up here. So that's our carry in. Let me turn this off. Now we can do, so I have these functions built into here. So if I wanted to do, say, let's delete this again, and do 3 in this, and 5 here. Okay, so we're going to do 5 plus 3. Got 8. Now what I can do is do it the lazy way. So if we want to subtract, flip that on, now do 5 minus 3, and we get 2. And you can see that the carryout is on, saying that it's positive. If we wanted to, we could OR those numbers together. So 5 OR 3 is 7. So if we were to OR them, we should have a 7 on the output. And we do. Okay. What if we did NOR? Well, then it should be everything but 7. So it should be the inverse of 7. Oh, that looks good. Okay, what about AND? Well, that should just be 1. Because 5 and 3 is 1. So let's do that. Ooh. Okay. What is the issue here? Let me figure it out. I think I know what it's not doing. It needs to be... It should be inverting A, and then it should also invert B, so this should also be tied here. And now we should have a 1. Yep, alright, now we have a 1. Okay. Oh, it's some stupid mistake like that. Now we do NAND, which should be everything but 1, because it's the inverse of AND, which that's off, and then all those are on, so that's good. If we, instead of doing NAND, let's do XOR, so that should be a 6 on the output. And then we have a 6, nice. Let's try XNOR, so that should be everything but 6. So like inverse of 6. Which looks good. And then we should have a right shift, which should just take our sum of 8 and shift it down to be a 4, which it did not do. That's because this right shift isn't hooked up. So the right shift gets hooked up here, like that. And now we have a 4. So now we can turn on and off right shifting. And so like, let's just put in, say, the number 5, and I could right shift that here. And you see, we get a 2 and then like underflow. So we can shift the number down. So this will allow us to do any logical operation we want without a ripple within like 9 ticks, I think is the slowest it looks like. I think the fastest is 8 ticks, so I think it's 1 tick unsynced right now. But you could always just time everything to 9 ticks and call it sync. So yeah, this is cool. I have a way of, doing math, but now I need a way of storing these values. So I built this monster. So this is a D flip-flop in here. Right, here's a D flip-flop. And then there's 2 reads. And the way this works is the readout here, there's that read and the read above it. So there's 1, 2, 1, 2. It's 2 reads per level. There's 16 levels because this is 16 bits. And then we can see that we have 2 reads and 1 input. So what I can do is I could, let's say the ALU gave me some result of like 7. Let's say we did 5 or 3 and we got 7. Well, I could take that 7, put it in address 1, and write it. And then what I can do is I could read from address 1, like that, and get 7 out. And if I could read from address 1, I could read from address 1 twice, because I have 2 reads, and I can get a 7 on both. Let's say I put like a 31 into register 2. Well, now if I read a 2 here, you see that we have 31 on the left input and still 7 on the right. So then we can keep writing up to 32 different numbers into here, 32 16-bit values, and read up to 2 of them at once. So what this will do is now allow our ALU to be fed with 2 different values at the same time so that it can always write one back. And so this is a dual read register, and as you can see here, we're telling it one address here in one of the reads, and then another address here in the other read. And it's saying send those lines out. And it's doing that. Yeah, so that's that. And then this was what I had before I was doing those registers, and this is 14 bytes. So it's 7 registers of 16 bits. And then there's 2 of them, and they hold the same data. So this is simulated dual read, where that's actually dual read. So that's a lot more dense and holds a lot more data compared to that, which just holds 14 bytes. That's holding 64 bytes. Yeah, 64 bytes there, 14 bytes there. And you can see the reason this is bigger is because it allows for, it has these snapping pegs, which allows you to tile it. This didn't really allow you to tile it. You had to build most of it by hand, unfortunately. So it took a lot of time. So my goal now is to make a CPU, and the way that'll be done is I need a way to decode instructions. So you basically have some instruction ROM here, and you can power this by, say, have a switch like this, and then when that line is on, you can encode values by connecting them to those pegs like that, and then that sends downwards and allows the data to just be a ROM. So this will allow you to encode what you want by connecting the wires and then reading them through. And it's just basically diode ROM, diode matrix ROM. It gets to how you do it in real life, well, with diodes. And then here is just a decoder, a vertical decoder. So there's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So then what this will do is it'll take all my different instructions coming in, and it'll say, oh, instruction 1 has this format here. Or instruction 0, sorry, has this format for bits. Instruction 1 has this format for bits. Instruction 2 has this format, and then these can go to whatever they need to control. So you can map each instruction to what it needs to do individually, and then that's how you control the ALU and the registers. And of course, then I need to build a big RAM bank still for this. But yeah, I don't know if I want to actually wait till Logic World comes out in October, or whenever it's coming out, or build the CPU now. And I have some pretty ambitious goals for the CPU, so it's going to be a MIPS RISC-V style CPU, and it's going to be balls to the wall in terms of what it can do compared to what I've built in Minecraft, because, you know, this is actually speedy. And this is what I was going with, but I'm going with a bit of a different ISA now. I'm changing it to a 24-bit ISA, Harvard architecture. So for this first CPU, it's just going to be a ROM-based CPU, so everything's going to be stored in ROM like a microprocessor would do. And then I'm going to write. Actually, I'm going to borrow some programs that other people have wrote that allow you to convert like text files to like ROM files in the game. Like you can generate a ROM, and then what that'll allow me to do is then just write a compiler, fill a ROM file, load that ROM into a game, and then paste it in front of my CPU and connect it in, and I should be able to run any code I want while coding that code from my computer without having to be in like a game and connecting one wire at a time. So I could write code in C and then compile it down to RISC-V and convert to assembly and then machine code and then make a ROM. So that's the goal for this, is to not actually have to place any wires in game when you're coding the ROM. You can just code it like you would C or C++ or something like that. But yeah, that's my ambition so far. And I hope you guys like this video. I do have a few more things I could show you, I guess. So for the bonus video, check this out. Okay, so what I want to show you now is some stuff that I was preparing for the bresenhams unit that I was going to make. So in bresenhams, we needed a way to turn a value, like make it absolute value. So the way to do this, in my opinion, looks like this. So like, let's say we have, I'm just going to put some inputs here, like this. Just going to use a few bits, not using all of them. Shit. Alright, so let's put in, like, say the number 3. So the number 3 comes through. Alright, but now let's say the most significant bit was on. And let's say we're doing a signed value. Well, now it's going to think this is the number negative. This is negative, and it's going to convert this into a 2's complement value. So when, well, it won't. Sorry. Let me do it like this. So this is just going to pass through values, right? So I could put in. Let me do 3, and then plus that's 128. So that's 131. So we have the number 131 coming through. And then what I can do is I can say, take the 2's complement of that number. So that's the 2's complement of 131. Or what I can do is I can tie that bit there like that. So now I can say take the absolute value of a number. So we have the number 3 coming through. Let's say we were doing negative. So that is 0. No. Hold on. Let's take 3 and perform 2's comp on it. So to take 3 and perform 2's comp on it, we're going to invert and add 1. So we're going to take all these and go like this. And then we're going to add 1 here like that. Now, since this is saying that this is negative 3, and because it knows the most significant bit is on, and we're working with a signed value here, it's going to then, because it's passing through here like this, it's going to convert this value to 3. It's going to perform 2's comp on negative 3 and get the value 3. And, oh, I never hooked up these bits. There we go. And now we get 3. So I could say, do this, just pass through the value when I want. You can then take the absolute value. So that's what this is doing. When you flip the switch, it takes the absolute value or the 2's comp. Okay. Or no, yeah, when you flip the switch, it takes the 2's comp. But when you tie this to the most significant bit, that's when it takes the absolute value of a number. So when you put in something positive, it's not going to convert that positive number because, it's positive because the most significant bit is off. But the moment the most significant bit is on, it's going to treat it as a negative number and then do 2's complement on that. And so I can show you what's inside here. So if we clone this board, V move board bam V move board bam. Yeah. So this is all it is. So here's an XOR gate. There's an instant carry mechanism here, but it only works. You can't build an adder out of this because there's no instant cutting mechanism. So that's why I asked the developer of this game to add kind of like a way to cut wire, but the wire would cut instantly, but you could have delay on how long it took to actually operate that device. So it wouldn't be 2-op, kind of like how pistons in Minecraft can retract instantly, but it takes time to then power them back up the other way. Some sort of similar mechanism, but no moving parts would be cool for here, because then we can have a whole adder would be the size of this, and it would have an instant carry mechanism in between here. Whereas this can only add 1 because of the way the carry's done. But the way it does adding 1 is through here, and then it has an inverter here. So you can say invert all my inputs and then add 1, and that's how you do 2's complement. So that's how that device works in that red there. Then I built a double buffered counter. So this game has a lot of issues with micropulses, or not micropulses, but just button pulses, and it'll just start looping randomly. So I wanted to prevent that as much as possible, especially on something that's going to be counting. You don't want to have any issue with it. So I built this thing here, and you can see that. Oh, I guess you can't tell. So this is a register. Here's a D flip-flop, a D flip-flop below it. So this is a register, and then the register goes back in. So this is using that incrementer circuit over there that I built without and it's got the inverter in the front here. So what I can do is I can either add or subtract a value, and then I can because of that I'm able to, or I can either add or subtract 1, so I can count up or down because of this. So I ended up putting it in a nice shell like this because it's hard to just look at all that crap. So you just kind of want a shell where you can say, where are my inputs and where are my outputs? So here's your outputs. So you have output 0 through output 7. I should have labeled them Q instead of O, but whatever. Then you have some branch inputs here. And then here's just a copy of those outputs again. It's just a second-hand output. It's just redundant from there, just if you wanted it on where the branch input is coming from. Then you have the clock up there. You have an enable. And then you have an increment or decrement. And then you have a force 0. So force 0, and you clock it. Oh, I guess you'd have to enable it too. There you go. It put the output at 0. So what we could do now is we could say branch to line 30. We're going to take off force 0. But we're going to... Oh, maybe no. I think But I think force 0 has to be on when we do a branch. And we clock it, yep, okay. So force 0 allows us to branch. And now we have that value in the program counter. So now what we can do is we can say, oh, that's a button that needs to be a lever. What is it? Maybe it was, and I was just looking at it weird. Okay, so we're going to be incrementing it because it's 0. So if I clock this, it went to 31. And if I clock it again, oof, that is not working. I think I know why. It's because I had the branch input still on. Yeah, okay. Yeah, you have to clear the branch inputs. I didn't make any way to automatically do that. I can, but I didn't. So I'm going to branch back to where we want to be. Turn off that. You just put an AND gate with that, with those inputs there. And then that's how you can enable the branch to work properly without screwing it up when these are on. So now that that's not on now, we can count up one at a time. And you watch when it, so from here, when I click it, it's going to be synchronous when it rolls over. So there's no ripple in this counter. And you see it's double buffered, so even though it's screwed up a little bit, like you can see it flashing if you go too quick on the input, it still is it managed to count without getting interrupted. Yep, and then so what we can do, so we can enable decrement, and it's still synchronous. Watch it, it's going to be synchronous. Boom. Yeah. So, and then yeah, we could just force 0. Because when you force 0 and you don't have a branch input, it's just going to force it to 0. I guess I should change that to enable branch. There we go. So that's going to be enable branch. So then here's where a few previous iterations that weren't double buffered, so it didn't work near it. Oh no, this is just a count. This is just combinational. So this isn't sequential. So there's no clock on here. So you can just, if you put in a number, you can either ask for the number above it or the number below that on the output. So it's like the counter, except not being hooked up in a data loop. So if I just like hook up a pin here, oops, this be a switch. Yeah. And if I push that on, it passes through, and then I can say what's above that or what's below that. So I could enable it, and now it counts up one. Or I could say no, what's the number below that? And they'll say, oh no, 3 is below 4, or 5 is below 4, above 4. So I could tell you the number before or after another number, and then so I just use that in this thing. Just had it feed back into itself, double buffered. And then we have a conditional, or we have a compare unit here. Or this is an adder, sorry. So this will just add 2 8-bit values and output there, so everybody knows how an adder works. And then here's a compare unit. So this will tell you A is greater than B, less than B equal to, and it gives you the flags carry out and 0 just in case you want them yourself. Here's the subtraction output, because you don't need to use it as a comparator, you can just use it as a subtractor. So you can put in, say, oops, no, this is the least significant bit, so I'll put in 5. Right now we'll do 9 minus 7, so that's 9 minus 7. Like that. So 9 minus 7 is 2. And it's not telling us. Why isn't it not telling me? Uh-oh, it's video. I even get in there to... Oh yes, I can. What is my Z? Okay. Oh, I mean, it would help if I hook these things up, right? Turn that back on. There's that flag. Carry out. That's the carry out flag right there. Which makes the other one if 0. There we go. Alright, so it's telling you A is greater than B, and then those are your 2 flags that you get out of it. And was A greater than B? Well, A was 9 and B was 7, so yeah, A was greater than B. So like, if you wanted to, you could make B bigger. Flip this on. Now you're going to get a negative value, most significant bits on. So now you have a negative value here. And it tells you for the flags here that A is less than B, and you have a 0 flag. Well, you have a not 0 flag. If that's on, it means it's not 0. If it's 0, then it means it's 0. The carry out, if that's on, then there's a carry out. If it's off, then there's no carry out. So right now, we know that A is less than B, and if you made the numbers equal, like let's just put in 3 and 3. It tells you A is equal to B, you just have a carryout flag, and there's a 0 there. And there's a 0 on the output, so it shows you that there's a 0 on the output there. So that's all the 0 flag is. So now this can compare 2 numbers you're subtracting. And basically that's all you need for bresenhams. It's just a couple up-down counters, an adder-subtractor, and then a conditional adder-subtractor. And yeah, that's basically all you need. So let's just show you some stuff I made recently, and hope you guys enjoy, and I'll see you guys next time. Peace.